In section 5.8, we're going to talk about Fibonacci sequences. So in this chapter section, you will learn about Fibonacci sequences. Those sequences are additive, and we call them typically a recursive type of sequence. A recursive sequence is one in which the number in the sequence is an addition of two previous numbers in the sequence. For example, if I started out with 2 and 3, the next number in the sequence would be 5. The next number in the sequence would be 8. The next number in the sequence would be 13. This sequence is very similar to the Fibonacci sequence in that I've started with two seed numbers that are very similar to the Fibonacci sequence. This type of sequence then is a recursive sequence. That is, AN is equal to AN minus 1 plus AN minus 2. The Fibonacci sequence is named after Leonardo da Pisa, also known as Fibonacci. He was one of the most distinguished mathematicians of the Middle Ages. He is also credited with introducing the Hindu-Arabic numerical system into Europe, and he wrote the first algebra book. So the Fibonacci sequence starts out with what we call the first two seed numbers. In this case, it's 1 and 1. So once we have the two seed numbers, the next number in the sequence is just going to be added of the first two previous numbers. So in this case, 2 is the third term in the sequence. Then 3 is just the addition of 1 plus 2, which is the fourth. And now the fifth is the addition of 2 plus 3, which is then 5, and so on. In the middle of the 19th century, mathematicians found strong similarities between this sequence and many natural phenomena. The numbers appear in many seed arrangements of plants and petal counts of many flowers. Fibonacci numbers are also observed in the structure of pine cones and pineapples. The golden number is the following: the square root of 5 plus 1 divided by 2. The value obtained from the ratio of the n plus 1 terms to the nth term proceeding in the Fibonacci sequence as n gets larger and larger. The number for the golden number, the symbol for the golden number, is the Greek letter phi, which is phi. To give you an example of how the ratio works, we notice that in the sequence of 1, 1, 2, 3, 5, 8, 13, that if I took the ratio of 8 divided by 5, we get a number 1.6. If we take the ratio of 13 divided by 8, we get the number 1.625. As the sequence gets larger, the next number divided by the previous number gets closer to this golden number. So in terms of the golden ratio, we look at a line segment. And in this line segment, we have the line segment AB, AC, and CB. The ratio of the whole AB to the larger part AC is equal to the ratio of the larger part AC to the smaller part CB. AB ratio to AC is referred to as the golden ratio, but also AC to CB is also referred to as the golden ratio. So now the ratio is, the golden proportion or divine proportion is AB to AC is equal to AC to CB. And this equals, guess what? The golden number. So in looking at how the ratio actually works, we draw a line and we have a point A and a point B and a point C, such that the distance between A and C is called x. The distance between A and B is 1 unit. And then the whole unit, AB, is equal to x plus 1. So now you can see how the ratio works. AC is equal to x, and obviously CB is equal to 1. Now if you substitute these numbers into the ratio, you will see that when you solve for x, you get, in fact, the divine proportion. So if we look at the Great Pyramid of Giza in Egypt, built about 2600 BC, the ratio of any side of the square base to the altitude is about 1.611, which is approximately the golden ratio. So the golden ratio in the human body. Architect Le Corbusier developed a scale of proportions for the human body that he called the modular. You can see that how the ratio works in different portions of the body. Here again we have what's called the golden rectangle, where we have a rectangle which has a square, A squared, which is in the green, and then we have a rectangle which has the length of A and the side of B, and that is in a golden proportion because the length divided by the width, which is A plus B divided by A, is equal to A over B, which is in the golden ratio form, gives us, when we solve for it, we see that we get the golden ratio. The golden rectangle in nature we can see in curved curves derived from succession of diminishing golden rectangles is the same as the spiral curve of the chambered nautilus. The golden rectangle in Greek architecture, the Parthenon, is also in the golden ratio form, and it was done so on purpose. In fact, Greek statues, vases, urns, and so on exhibit characteristics of the golden ratio. It is Phidias, considered the greatest of Greek sculptures, that the golden ratio was named Phi. The proportion can be found abundantly in his work. The proportions of the golden rectangle can be found in the work of many artists, from the old masters to the moderns. So Fibonacci numbers in music, an octave on a keyboard has 13 keys, 8 white keys, 5 black keys. The 5 black keys are in one group of 2 and one group of 3. Western music, the most complete scale, the chromatic scale, consists of 13 notes. All are Fibonacci numbers. In music, patterns that can be expressed mathematically in terms of Fibonacci relationships have been found in Gregorian chants and works of many composers including Bach, Beethoven, and Bartók. A number of 20th century musical works, including Ernest Kernek's Fibonacci Mobile, were deliberately structured using Fibonacci proportions. So why are we studying the Fibonacci sequence? A number of studies have tried to explain why the Fibonacci sequence and related items are linked to so many real-life situations. It appears that the Fibonacci numbers are a part of a natural harmony that is pleasing to both the eye and the ear. In the 19th century, German physicist and psychologist Gustav Fechner tried to determine which dimensions were most pleasing to the eye. Fechner, along with psychologist Wilhelm Wundt, found that most people do unconsciously favor golden dimensions when purchasing greeting cards, mirrors, and other rectangular objects. Well, that concludes our chapter in 5.8 on the Fibonacci sequence. Both 5.7 and 5.8 were on sequences. Please study these, and I hope you found it very interesting.